Okay, there we go. All right, here is the solution for quiz 1. Whenever I'm doing these capacitors and inductors, the first thing that you want to make sure that you understand is that there's a switch. If I see a switch in exam 1, almost always it is a capacitor and inductor. And remember, the switch is saying that there's a steady state when it's open and a steady state when the switch is closed, right? So in a transient, which is all these inductors and capacitors for these DC problems, is a transient problem going from one steady state to another steady state. And this arrow is the transient equation. And so the first steady state, if I'm reading this problem statement, it says VC, the voltage across the capacitor, is 10 volts prior to t equals 0. So that means it has a charge. This is my V initial. V initial equals 10 volts. I don't even have to solve for it. So then at time equals 0, the switch closes, right? And now it's a part of the circuit. And then we'll analyze that in a second. Let's see what's being asked for first. How much energy is stored in a capacitor prior to the switch closing? Well, prior to the switch closing, it was at 10 volts. Energy equals 1 over 2CV squared, right? Energy is in joules. Energy is in joules. 1/2 capacitance is the 6 microfarads from right here. C equals 6 microfarads. And the V is that initial voltage because it wanted to know prior to the switch closing. It had 10 volts squared. And that comes out to 300 millijoules, or is it microjoules? 600 microjoules. Okay. Next step is calculate the steady state voltage across the capacitor when the switch is closed. Now here's an example where it is maybe helpful to redraw. I have a current source and I have these two resistors. My switch is closed. I have a resistor over here, but a fully charged capacitor looks like a what? An open, right? It has no more room on the plate for the electrons, like the parking lot attendant. Quit sending electrons to me. I don't have any more space. And it opens it up, but there is a full parking lot with a voltage across it, right? So there's stored energy of this capacitor, VC. And so it's been opened up. So now whenever I'm analyzing this, and I'll label these nodes in blue, what I'm saying is what is the voltage from this node to this node? And watch, I go past that resistor because there's no more current flowing through it. It's an open circuit, so no current flows through this resistor on the right. So just like when we have our voltmeters and I plug in a voltmeter across something, right? I'm plugging the voltmeter in across this, no current flows through. In the real circuit, this is still an active circuit, and there's current going through like this right here. And so if you need to draw little dots or imagine the current going through like we have in the simulator, the current is going through that, it's not going through the one on the right. And so because this is a current source, V equals IR, and I want to know from the blue node to the blue node, well, between those blue nodes, the R is just this 2 kilo ohm, right? 2, what's that, 5? But all I care about is that first 2. The 2 on the right is dead. The 5 doesn't matter because I want to measure between the blue nodes. And the I is 1 milliamp, and it comes out to 2 volts. So this is my V final, the steady state that it reaches after the switch is closed. So it was at 10 volts, it's going down to 2 volts. So it is discharging, but it's not fully discharging. If I was to draw this on a graph, right, as a function of time, what is the voltage across the capacitor? It was at 10 volts for a very long time. And then we close the switch right here at t equals 0, and it goes down until it hits a steady state. And that steady state is 2 volts. Okay? And right here, the amount of time that it takes is 5 tau. And so what is that tau? The tau is RC, and it is Thevenin of the final circuit, which is pretty obvious if I think about the graph. My final circuit is on this side. Well, this tau is a measurement of how quickly is it going down. And so it's after t equals 0. So the R Thevenin is from the final circuit. How do I do a Thevenin? Once again, it's helpful to redraw. I zero the R, for an R Thevenin, I zero the source. Zero current is modeled as an open, right? And then I have 5 volts, or sorry, 5 kilo ohms, 2 kilo ohms. And then here, between where the capacitor was, I'm looking at the R total. What is the R total looking back this way? Once again, it might be helpful to imagine an ohm meter sends current through and it only goes this way. Nothing goes to the 5 because when I opened the circuit by zeroing the source, nothing was there. And so I have 2 plus 2, 2 kilo ohms, 2 kilo ohms, and my R Thevenin equals 4 kilo ohms. So I can plug those in. Tau equals 4 kilo ohms. Capacitance is 6 microfarads. And tau equals 24 milliseconds. So when I plug it into the equation now, and it's helpful, I think, to always write the equation before we plug in values. V final plus V initial minus V final, e to the negative t over tau. That is the equation of the graph that I've drawn on the right. So the VCT, V final is 2 volts, the initial 10 minus 2, e to the negative t over 24 milliseconds. I wanted to simplify it one more time. 2 plus 8 e to the negative t over 24 milliseconds. The last step, calculate the voltage across the capacitor at t equals tau. So what this is saying is, if I plug in tau here, e to the negative 24 over 24, or if you recognize that it was 1, you could write e to the negative 1. And I think it comes out to like 4 point, I don't have my calculator, I think it's like 4.79, 4 point something. I'll have it in the PDF whenever I upload the solution. But there is my V, the voltage across the capacitor, which makes sense. It should be between 2 and 10, right? If it was going from 10 down to 2, look how quickly at 1 tau, it went all the way down to 4, which also lines up with this graph, that the graph drops down quickly, right? I'm trying to, and then it slowly dissipates the last bit. And your phone even charges this way. If you look at how your phone, you plug it into the wall, it charges, if it's at like 30%, it'll get up to 80% much faster than it'll get from 80 to 100%. Sometimes you may even look at your phone, you're like, man, I feel like it's been charging at 96% forever. You know, that's this curve that's taking forever to finally hit its true steady state of 100% charge. Let me stop the recording and then